Hi everyone, I wanted to go over how to isolate and write half reactions out of a redox reaction. So this is a follow-up to the video on half reactions by the other teacher that I posted. This is a shorter version. So the key things you need to be able to do here is you need to be able to figure out oxidation numbers, which was the very first part of this chapter. You also need to know the definitions of oxidation and reduction, and how to use the oxidation numbers of elements in a chemical equation and the definitions of oxidation and reduction to identify the element that's being oxidized and the element being reduced. Okay? Once we have those three things in place, we can then isolate the oxidation part, we can isolate the reduction part, and we can write them as two separate half reactions, because you cannot have one process happening without the other. There needs to be a source of electrons. That would be the thing that's being oxidized, because it's going to lose them, right? It's going to get rid of them. It's the source of electrons. And there needs to be a place to send them to. The thing that's getting reduced is going to obtain the electrons. You can't just leave them on a park bench and be like, bye, electrons. You need to actually transfer them from the substance being oxidized to the substance being reduced. Let's look at this do now question. In the following equation, what is the oxidizing agent? So in an earlier lesson, we looked at these definitions. An oxidizing agent is a substance that allows something to be oxidized. If it's allowing something else to be oxidized, then that means itself is being reduced. So we are looking for the substance that's being reduced. So anytime you see something that's asking you about an agent, the process that you're looking for is the opposite process. So for this do now question, we will be taking care of these first 2 points. Okay, oxidation numbers, and then defining oxidation and reduction. Actually, and a third one too. Okay, so a shortcut for this is if you see a polyatomic ion that's present on both sides of the equation, then you know that the nitrogen and the oxygen aren't doing anything. They are spectator ions, okay? So it's not going to be oxidized or reduced. I'll do the numbers for it anyways, just for the practice, but those are not going to be involved in the reaction. Why aren't you erasing? Cute. Okay, so let's look at oxidation numbers. So for copper on the reactant side, since copper is by itself, its oxidation state's going to be 0. And then if you look at the silver on the product side, since that's by itself, it's going to be 0 as well. All right, now this NO3 is a nitrate ion. On table E, where your polyatomic ions are, nitrate has a -1 charge. So because this nitrate unit has a -1 charge, and there's one of that unit, that means that the silver has to have a +1 charge because there's one of it, and that whole thing has to add up to 0. On the right-hand side, the nitrate's still there. That's still going to be a -1 for that unit, and there's one of it. So that means the copper is going to be a +1. So let me just clean this up real quick. Why won't this erase? This is so weird. So let me clean up this equation with the numbers so we can see it a little bit better. So we have a 0, we have a +1, nothing's going to happen here. We have a +1, nothing's going to happen here, and this is a 0. Incidentally, this is a +5, and these are each a -2 if you calculate them out, but you don't need to worry about it because they're not changing. Okay, so that's the first step, figuring out oxidation numbers. Now, the definitions of oxidation and reduction, we're losing electrons, we become oxidized, we gain electrons, we become reduced. So let's look at what's going on. We have copper going from a 0 to a +1. We have silver going from a +1 to a 0. So if copper is going from a 0 to a +1, how does it, in terms of electrons, what is it doing? Is it losing an electron or is it gaining an electron? Well, if it's becoming more positive, it's losing an electron. So the copper is being oxidized. That means that the silver, since it's going from a +1 to a 0, that means it's becoming more negative. It's gaining an electron, it's getting reduced. So this question, what is the oxidizing agent? What substance is being reduced? This silver, +1, is being reduced from a +1 to a 0. Okay, so all of that to answer that one, that's a Regents question. Okay, so when you're looking at these processes, so let me just rewrite this equation real quick. When you are looking at the processes of oxidation and reduction, in an equation, you can isolate the two halves, right? So a half reaction is going to show either the oxidation part or the reduction part. A reduction half reaction shows an atom or ion gaining one or more electrons, and an oxidation half reaction shows an atom or ion losing one or more electrons. Okay, so this is in terms of Leo says Gar. So based on what we saw in this example from earlier, if I wanted to write the reduction half reaction, I would take the silver and write down how it starts, +1. I would show how it ends, 0. Now, a half reaction is not complete until you put in how many electrons are involved in the process. So since reduction is the gaining of electrons, it's pulling more electrons towards it, I would have to add 1 electron to the left-hand side, because a +1 plus a -1 equals 0. Okay, so for a reduction half reaction, the electrons, 1 or more electrons, is always going to be on the reactant side, because charge-wise it would balance out. If I wrote it this way, mathematically that doesn't work. Look at our charges. +1 equals 0 plus -1. Like, no, that's not, I mean, I'm no math major, but you know. Now for the oxidation half reaction, we have a similar thing happening. We have copper starting out as a 0 and changing to a +1. Now, because it's losing an electron, we will add it to the right-hand side. We don't want to subtract things. We never use subtraction signs in chemical equations. So yes, even though like this, mine loses an electron and becomes positive, mathematically works, we don't show subtraction in equations. Instead, we will just add it to the opposite side. So mathematically, look at our numbers. We have a 0 equals +1 plus -1, and mathematically that does work. So this is the half reaction for reduction, and this is the half reaction for oxidation. So let's look at a couple more examples. This is just a step-by-step process, but I basically just walked you through that. So you have to do your oxidation numbers, you have to identify what element's being oxidized, you write down how it starts and how it ends. Same thing with reduction, write down how it starts and write how it ends. And then the newest piece, the only real new piece here, is show how many electrons are involved in the oxidation or reduction half reaction. Oh, just did that. Okay, so let's actually look at this second one first. I think that's a little easier. So we have to do our oxidation numbers. So we have magnesium by itself, it's going to be a 0. We have chlorine, Cl2 is by itself, it's a 0. It doesn't matter what the subscript is. If it's an element that's not in a compound, right? Compound means different elements combined. It's just going to be a 0. It could be Cl52, like who cares? It's going to be a 0 for the oxidation states. Now, in a compound, we have a rule for magnesium. Magnesium is a group 2 metal. All group 2 elements will have a +2 oxidation state. Now, if this has a +2 oxidation state, what does each chlorine have to be in order for this whole thing to add up to 0? So we have +2 times 1 equals +2. Whatever gets added to it has to equal 0. So that means this has to add up to -2. Well, if there's 2 chlorines, each chlorine has to be a -1. So you could think of it as reverse crisscross. There's the 2. There's a 1 here, so here's their -1. Okay? That doesn't always work, but okay. So let's look at the processes now. We have magnesium changing from a 0 to a +2, and we have 2 chlorines changing from a 0 to a -1. So let's write down what's happening with the magnesium. Magnesium's going from a 0 to a +2. So what process is that if it's going from a 0 to a +2? Is it gaining electrons or losing electrons? Well, that would be losing electrons, and losing electrons is oxidation. Now, when I lose electrons, I want to add electrons to which side of the equation? If they're being released, I will add them to the right-hand side. And since this charge went from a 0 to a +2, that means that 2 electrons were released every time a magnesium atom was oxidized. that means, because we only have one other element here, that the chlorine is being reduced. So this is kind of unique now because of the way we have to write it. So the way that the chlorine starts out is Cl2, right? Just plain old molecular chlorine. And now we want to show the two chlorines changing to a -1. Now it's important that you kind of swing this subscript over, because if you did this, what you're saying is that I have two chlorines stuck together with a -1 charge. What this is saying, which is what we want to say, is that there are two chlorines, each with a -1 charge apiece. So if I have two chlorines starting out with 0 charge, and each of those chlorines changes to a -1 charge, how many electrons had to be gained? Well, 2 electrons had to be gained in order to drop them down 2 charges. So those are the half reactions for that. For this first one, the charges are written in for you, and for the products, they're going to be zeros because they are alone, they're not in compounds anymore. So we have mercury starting out as a +2 and changing to a 0. And we have 2 iodine -1s changing to 2 iodines at a 0. So what is going on with the mercury? Which process is the mercury undergoing? Is this being oxidized by losing electrons, or is it being reduced by gaining electrons? Well, since its charge is going from a more positive number and moving in the negative direction, that means that this is being reduced. By how many units? 2 units. So 2 electrons were gained. So that means that this has to be oxidation, and we know the electrons have to be added to the right side. Well, if this mercury is gaining 2 electrons, then these 2 -1 iodines are each losing 1 electron to become 0, so a total of 2 electrons are lost. That's conservation of charge. The number of electrons lost has to be equal to the number of electrons gained. The last thing I want to look at here, and this was not covered in that first video, was how to balance half reactions. I'm going to show you a shortcut because this is kind of beyond what you really need to worry about. This was a Regents question. So given this reaction, what equation is properly balanced using smallest whole numbers? What's the sum of the coefficients? So you've seen those balancing questions before with sums of coefficients, but not written in this way. Now, this equation is kind of weird because when you look at it, you're like, oh, well, there's 1 magnesium on each side and there's 1 chromium on each side. So isn't this balanced already? But it's not. When you see these like little basic looking equations that have charges written in it, what they're showing you is the net ionic equation. What they're doing is they're leaving out the spectator ions. They're only showing you the elements that are changing in oxidation state, and they're ignoring anything else in the reaction that's not changing. So here's the really easy way to do this. We're going to make 2 little brackets here. So magnesium went from a 0 to a +2. So is it gaining or losing electrons? That would be losing. Well, how many did it lose? Well, it doesn't have a charge next to it originally, so that means a 0. So it went from a 0 to a 2. That means it lost 2 electrons. Now look at our chromium. Our chromium started out as a +3 and it went to a 0. So it gained 3. Now, if you look at these and they are not the same, then this equation is not balanced. And we need to multiply one or both of these elements by some number that will get those electron numbers equal to one another. So that's 2 electrons, 3 electrons. So if I have a 2 and a 3 in an equation, what can I make them both equal to? I can make them both equal to 6. So in order to make this part equal to 6, I multiply everything by 3. In order to make this part equal to 6, I multiply everything by 2. So basically what I do is I take that number and I write it in as a coefficient in front of both of those elements. It has to go with both of them, right? I can't put a 3 in front of one magnesium and not the other. And then I put the other multiplier, the 2, for the chromiums. So now look, we have 3 magnesium zeros changing to 3 magnesium +2s. So that's a total of 6 electrons being lost. We have 2 chromium +3s changing to 2 chromium zeros. That's by gaining 6 electrons. So this is the same on both sides. I have the same number of chromiums on each side. I have the same number of magnesiums on each side. So that is balanced. What's the sum of the coefficients? To answer the actual question, well, the sum of the coefficients would be 10. For this question, balance the redox reaction. If it doesn't tell you to do like electrons and stuff, just balance the equation. If they give you a whole equation, you balance the equation. So you just throw a 2 here and a 2 here and you're done. Bye. So that's it for the first part of this unit. It's really important that you understand what oxidation is and what reduction is in terms of electrons. Have an understanding of how to use table J, that activity series. Metals that are higher up on table J are more easily oxidized than the ones that are further down, and non-metals that are higher up are more easily reduced than ones that are further down. Because the second half of this chapter, we're going to take this idea of moving electrons and put it to work, and talk about electricity and batteries. So stay tuned. I know you are thrilled.